talked about normal approximations, right? So first we talked about the normal distribution, and then we talked about the idea of approximating different distributions with normal distribution, right? So this is a very important topic of this course, right? Many chapters in this course are related to the normal distribution. And I think it's pretty fair because the normal distribution is the most important distribution, in my opinion, in the universe, right? And it's fairly, reflected in the book. It's most part of the book is normal distribution, right? So you have to learn this material very well, right? So we mentioned that this is where we ended the last class. We mentioned that the binomial distribution can be approximated with the normal distribution if basically if n is large, right? So you see that if n is large, these inequalities hold, right? So if you have many experiments, then np and n times 1 minus p are both going to be more than 5. And I also mentioned that the Poisson distribution, in fact, is the same thing as the binomial distribution, right? So Poisson is a special case of binomial when, you have infinite number of experiments and the chance of every experiment is very small. That becomes Poisson, right? But in any case, Poisson can also be approximated with the normal distribution if lambda is large, right? So that means that, if in average you expect many events to happen, for example, if you're looking at the number of customers who enter Tim Hortons in an hour, and that number in average is, 20, right? Then you can assume it's a normal distribution, right? Because the Poisson distribution for lambda equal to 20 will be quite close to a normal distribution, right? Now, we will see basically how to calculate that normal distribution, right? So what are the parameters of the normal distribution that approximates a Poisson distribution or a binomial distribution? Right? And we also looked at this graph in the previous class. So these are different binomial distributions. Here in this binomial distribution, probability of success is 0.4. And here we see basically different ends, right? So this is just plotting the binomial for different ends. And we see that, for example, for n equal to 20, this curve is almost a Gaussian curve, right? Okay, so how can we do that, right? So I just mentioned that we can approximate a binomial distribution with a normal distribution. How should we do that? This is the equation. This is the equation to do that, right? So the equation is your random variable minus np divided by square root of np times 1 minus p. Does this equation look familiar to any of you? Have we seen something like this before? What is it? It is something simpler. So what is NP? NP exactly is the mean, right? And does anybody remember what was NP times 1 minus P? It's the variance, right? And the square root of variance is sigma, right? So in fact, this equation is x minus mean divided by sigma, right? So it's the same equation that we saw before, how to make a normal distribution, a standard normal distribution. This is the same equation, right? So we are following the same procedure. We are subtracting the mean, and we are basically dividing by the standard deviation. And I told you in previous class that this is a very, very common approach, subtracting the mean and then dividing by standard deviation. Even in deep learning, this is done as the first step when you have data with, like your data can be quite different, with different means and different variances. The first thing we do is that we subtract the mean and then we divide by the standard deviation. So, you should, in my opinion, you should really memorize this equation, x minus mean divided by sigma. It is in the crib sheet, but it's a very fundamental equation. So So there's one small, it's unfortunately not as simple as this. There's one very, very small, modification that we have to make, and that's called the continuity correction, right? So it's just a small 0.5 that we need to add, right? So if we want to calculate probability of x being less than something, then when we approximate it with the normal distribution, we have to add x. We have to add 0.5 to x, right? And if we want to calculate probability of x being more than something, then we have to subtract 0.5, right? So for now, just accept this is correct, right? Let's basically get the big picture of what's going on. I will explain later on why we add 0.5 and subtract 0.5. Sometimes it doesn't matter if you do that or if you don't do that, you get the same answer, right? Because 0.5 sometimes is such a small number that it doesn't change the result, but sometimes it does change the result. So I encourage you to always do it. So basically the idea is, if this is my x, my random variable, and basically I want it to be more than some x, less than some x, then so basically in the discrete case, I want my x to be x or x minus 1 or x minus 2, right? Or so forth, right? So for the case at the top, this is basically my my discrete case, right? So I want my capital X either to be x, or I want it to be x minus 1 or x minus 2 or so forth, right? When I convert it to the to the normal distribution, I want my x here. I just add 0.5. So this is x. This is x minus 1 and so forth, right? So when I convert it to some normal distribution, so let's say that normal distribution is something like this. I didn't draw it very symmetric. It should be symmetric, right? That's why I didn't do a good job. But the idea is you say x is less than x plus 0.5. So you just add 0.5 here. So this guy here is x plus 0.5. So we calculate this area. And for the other case, we subtract 0.5. So let's look at an example. It's not difficult. It's really easy, right? Okay. So in a digital communication channel, assume that the number of bits received in error can be modeled by a binomial random variable. The probability that a bit is received in error is 10 to the minus 5, so P, probability of receiving a bit in error is 10 to the minus 5. If 16 million bits have been transferred, so 16 million. Part A, what's the mean and standard deviation of number of bits in error, right? So part A is really simple. Basically, the question tells us that it's binomial, and it also tells us N and P. So mean is NP, and that's 160 bits. Right? And variance is NP times 1 minus P, and that's 159. Right? Or standard deviation is 12.6. Right? So we just said that the binomial distribution becomes the normal distribution when NP is more than 5, and also N times 1 minus P is more than 5. So in this case, NP is 160, and that's of course more than 5. And N times 1 minus P, for sure that's also more than 5. That's a very large number, in fact, right? Because P is close to 0. So this is approximately 16E6, right? So it's much more than 5. Right? So both of the conditions for approximating the binomial with the normal distribution are satisfied. So check, right? So it is a normal distribution. It's, so, right, yeah. Yeah, I am, yeah. Yeah, this time we have, yeah, thank you, but this time we have that. Last time, for some reason, we didn't have that orange dot either. This time it is going to work, hopefully. Okay, so basically what I'm going to do now is very interesting. I'm going to say that, you know, I don't care it was binomial. From now on, I'm going to assume it's normal, right? So what is the normal distribution? The mean is 160, and the standard deviation is 12.6. So that's it, right? So now my distribution is going to be this. So this is X, number of bits transmitted in error, and the mean is 160, and the standard deviation is 12.6. Right? Because I just calculated the mean and variance of this distribution. Right? So, and if we actually do plot the original distribution, it looks quite similar to this one, right? Because NP and n times 1 minus p, both of them are quite large. So the next part wants the probability that we have 150 or fewer errors happening, right? So I want 150, so in this curve, 150, let's say, is here, right? So I want this area under the curve, right? I want to have 150 or fewer errors. And we know basically this now. To solve this, we can use the lecture material on Monday. We did questions like this, right? We have the normal distribution. What's the probability that we are here, right? So the problem is sort of solved. Okay, so let's. So this is basically one solution. What I wrote here. Another solution is to use the equations, right? So let's use the equations that we just introduced. So probability of x less than or equal to 150 is equal to probability of x less than or equal to 150.5. So since we are saying less than something, I add the 0.5 continuity correction, right? And now basically I use that equation x minus np divided by square root of np times 1 minus p, right? This was the equation to convert binomial to normal, right? So basically probability of this happening is equal to, I'm going to basically apply this equation here, right? So NP is 160, and this is the denominator, right? And then this thing, if we compute it, this thing becomes minus 0.75. Right? And now we look at the table. I'm not going to switch to the table anymore. So basically just trust me that from the table for this value, minus 0.75, the number that we get is 0.22. Right? And it's always a good idea to do like a sanity check, right? So this guy here is negative, right? So remember the standard normal distribution looks like this. This is 0, right? Probability of something being less than minus 0.75, it should be less than 0.5, right? And it is less than 0.5. So we probably didn't make a mistake. So this is less than 0.5. Yep.
I just didn't understand
Yeah, yeah, that's a good question, right? So the question is, how did we move from x less than 150? That's what the question wants, right? The question wants 150 or fewer bits, right? Now the reason for that is that x less than or equal to 150 is in the discrete domain, meaning that x cannot be 150 and 5, right? X is integer numbers, right? But here, this basically, like, there's a problem with this book. This book is written for engineers, and the notations are not mathematically correct, in fact, right? So this x is not the same x, because this equality, as you said, is wrong, right? This can't be equal, right? So this is, so if we wanted to use the correct notation, this will be x in the discrete domain, and this will be x in the continuous domain, right? So these are two different x's, right? But since the book doesn't use that notation, I thought I might confuse you if we do that. But the idea is this is, now we have moved to the continuous domain, and that's why this number changes. Okay. Yeah. But I'll explain a little bit more why we add this 0.5. Other questions? Okay. Yeah, so basically we use the equation, but we could also use, remember we drew this thing here? We could use, we could follow with this, right? So basically I can compute this probability here as well, right? Maybe I do that, you see that why, these two things give us the same answer, right? So again, here I have to apply the 0.5 continuity correction. So since x here is continuous, instead of being less than or equal to 150, I'm going to move forward by 0.5. So I'm going to say I want my x to be less than or equal to 150.5. Right? So now I have a normal distribution with the mean of 160 and standard deviation of 12.6. This is mu. Right? I want the probability of x less than 150.5, and that's equal to probability of z. I'm going to make it standard, right? So remember, when we make it standard, x becomes z when it's standard, right? And this guy becomes 150.5 minus 160 divided by sigma, which is 12.649, right? This is z. Right? And if we compute this number, it's the same number that we computed before, minus 75. Right? So it gives us the same answer. So in fact, these two solutions look different, but they are exactly the same thing. I did the same thing in both of them. So in this slide, I used the graph, and I showed it on the graph. In the other slide, I used the equation. But they are the same thing. Any questions?
So can you use the integral to get it in this case?
What is it?
Can you use the integral in this case?
Integral? Yeah, that's a very good question. So basically, probability of z less than this, what we could have done is that we could have said, oh, okay, that's equal to, so this thing is equal to probability from minus infinity to 150.5 of, some coefficient, right? But what's important here, the coefficient is the constant number. So coefficient times e to the minus sigma squared. Sorry, not sigma squared. Can I delete here? No, I can't. So e to the minus x squared, and actually not, x squared. And it's a normal distribution. So instead of minus infinity to 150.5, I could use the standard case, right? So say from minus infinity to minus 0.75 of the standard normal distribution, which is minus x squared divided by 2 sigma squared, and sigma is 1, so 2 times 1, and dx, right? And this is x also, right?
Okay, so we can't use the 150 because it's a discrete.
No, we could use this one, but this one is easier because instead of minus infinity to 150, I could use that one too. But neither one works, right? So basically, so what I wanted to say was that this integral is impossible to do, right? In fact, if you could do this, you win the. It's impossible. Somebody proved it's impossible, right? So there are some math questions that they are conjectures, right? People think they are correct, but nobody has proven them, right? For this particular case, it is proven that you cannot do this integral. So don't try to do this integral in the exam because it's impossible to do. So that's why we use the table instead. Other questions? Yeah, but it's good to know, why you're doing this, right? So all of this goes back to this integral, and because we can't do the integral, we use the table. Okay. So that was approximating binomial with the normal distribution. If we have a Poisson random variable, and if the average number of events is large, meaning that is, for example, more than 5, then z is x minus lambda divided by square root of lambda. Does this equation look familiar? It's the same equation, right? It's in fact x minus mu divided by sigma, right? Same equation that I said is very important, right? Because for the case of Poisson random variable, lambda is mu, and square root of lambda is sigma, right? So in fact, for both binomial and Poisson, and for any distribution, right? Any crazy distribution, this equation is always correct. X minus mu divided by sigma. Any questions? So here again, we'll have to apply that, continuity correction. So if it's less than something, we have to add 0.5. And if it's more than something, we have to subtract 0.5. For now, just accept that we have to do this. I will explain why we have to do this. Yep.
So in the previous example, so we can't use the regular definition of the continuous random variable, the fx times dx, because it was a discrete function?
Yeah, so that's another good question. So the question is that here, in this question, when I write z less than something, I have already moved to, and when I'm in fact applying the continuity correction, I'm now in the continuous domain. So I'm no longer in the discrete domain, right? So we can in fact use the.
No, but I'm saying before we transform it to continuous, we can't use the integral.
No, before we convert it to continuous, yeah, you're right, we cannot do integral. And in fact, that's a very good question. So let's try to, let's try to solve this problem using the material we learned in the previous chapter, right? So, so basically, remember that probability of a binomial was x, basically combinations of x out of, x out of n, thank you, times p to the power x times 1 minus p to the power n minus x, right? So this is the probability of x for binomial, right? So what we could do in this question is forget about all of the normal distribution stuff and use, the material up to midterm, right? Say, oh, okay, I want to use this equation. I know this is the equation for binomial, right? So you want 150 or fewer errors? Okay, I'm going to do the summation. So I'm going to say, 0 bits in error. So 0 out of n times p to the power 0 times 1 minus p to the power n plus 1 bit in error, p to the power 1 times 1 minus p to the power n minus 1 plus dot, 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 plus all the way to 150 or fewer, right? So 150 out of n times p to the power, right? So you get the point, right? But the problem is that, first of all, we have to add up 150 terms. And the second problem is that, if you look at these terms, look at this term here. It's combinations of 150 from, what, 16 million, right? You can't even, if you even have a, very, high-end computer, you will get an error for this because this number is almost infinity, right? It's a very large number, right? Almost infinity is not correct, but it's basically combinations of 150 from, 16 million. Don't even think about calculating this, even on a computer, right? So, that's why we approximate these with, normal, because these numbers, even if you're, let's say, you might think that, oh, these are useless stuff because I usually work with a computer. I write a code to calculate this, right? You can't. Right? So every computer has something called floating point error. And when you add a bunch of numbers that are multiplication of, and this is not the end of the problem, this is just part of the problem. The other part of the problem is this number, which is almost infinity, is multiplied by p to the power 150, right? And when you look at p itself is almost 0, right? What was p? P is 1 e minus 5, right? So this number to the power 150 is going to give you 0, right? And any computer, when you multiply infinity by 0, the number that you get, it doesn't have enough precision, right? So you suffer from very, very large errors, right? So, you can't say that, oh, these are useless, I'm going to use a computer. No, you can't. You basically, the code that you write is going to give you very large errors. Questions? Okay. So same story for Poisson distribution, right? For the Poisson distribution, it's x minus mu divided by sigma, exactly same as binomial, right? And I showed you this graph before. We see that when lambda is large, the average number of events is large, the curve becomes the bell-shaped Gaussian curve. Right? Okay, so let's look at an example. Assume that the number of asbestos particles in a square meter of dust on the surface follows the Poisson distribution with a mean of 1,000, right? So mean is if a square meter of dust is analyzed, what's the probability that 950 or fewer particles are found? Right? So we want to calculate the probability of x less than or equal to 950. Right? So again, I'm going to use the equation P of x less than or equal to 950 is equal to, I'm going to apply the continuity correction, right? So since it's less than, I add 0.5. So P of, so, we can use correct notation. So this is discrete D, discrete x, sorry, and this is continuous x, less than 950.5, right? So I add the 0.5. And now I'm going to use that equation. Remember, was it x minus mean divided by sigma, right? To make it standard. So what I'm going to do is that I'm going to say, okay, this is equal to probability of z less than or equal to 950.5 minus 1,000, because the mean is 1,000, right? Divided by square root of lambda. So for the case of Poisson distribution, if I remember right, sigma was square root of lambda. Oh, square root of lambda, right? Is that correct? Yeah, okay. So divided by square root of 1,000. That's it. So I have my answer now because this is a number, and after this, I look at the table. So in my opinion, this material is much easier than the previous chapter because, once you get the hang of it, you just plug into the equation. You don't have to figure out which distribution you are, which equation to use. I think this is much easier material. Any questions? Yep.
You said that you were going to explain why it is 0.5.
Yep.
Right? Okay. Why don't we take 951?
Say that again. Why don't we take what?
951.
Oh, yeah. So that's too much correction.
Okay.
So the correction is 0.5. It's exactly 0.5. Yeah, I'll explain. Usually half of the students are satisfied with my explanation. That's enough. Other questions? Okay. Oh, by the way, we could actually use the Poisson distribution equation, right? So we could plug this thing. We have the equation of the Poisson, right? And we could plug in, okay, you want 950 or fewer. I'm going to plug in, from 0 to 950, and I plug into this equation, right? Again, the same problem as before. This is very, very hard to compute, even with a computer, right? Because why is it difficult? Because here you have, 1,000 to the power x, right? So this guy, when your x becomes large, you will have 1,000 to the power, for example, 950, right? That's a very large number, right? So you basically, and again, this guy is a very small number. So this guy is almost 0. And this guy is, almost infinity. Again, you suffer from this problem of 0 times infinity, and you suffer from floating point errors. Any code that you write is going to get you very, very large errors. So this is, in fact, the only solution, right? To approximate the Poisson with the normal distribution. So what we just did. Yeah, this is exactly what we did. 950.5 minus 1,000 divided by the square root of 1,000. Any questions? Okay. Yeah, we could actually do some, some sanity checks. So here it tells us that the mean is 1,000. So we could plot the normal distribution, right? 950 is here, right? The problem wants probability of less than or equal to 950, and the answer that we get is, a relatively small answer. It's 5%. Any questions? Yep.
So in the continuous domain, like we get a more visual effect of the mean and the variance. No?
We get a
more visual effect of the mean and the variance.
Yeah. Yeah, you're right. Yeah. Other questions? Okay. Yeah, so here's where I try to explain why we do that. This is not part of a course, right? So you can shut yourself off if you want. But I think it's important to know why, why we are doing this pesky 0.5 correction. So, actually one thing before I think I jumped too fast. So first of all, in the continuous PDF, P of x less than x is the same thing as P of x less than or equal to x. Is this correct, or I made a mistake here in this equation at the top? Yeah, it's correct, right? But it's a bit strange, right? So it doesn't matter if I say less than or equal to when it's a continuous random variable. Why is that? The reason for this is that P of x, exactly being x, is 0. Right? For the case of continuous case, right? So if I tell you that, for example, let's assume x is the time between two customers arrive, at Tim Hortons, right? If I tell you what's the probability that x is exactly 1 second or like 5 seconds or any number, that probability is 0 because it's never exactly, you know, that number that you want. This is a continuous number, right? So it's always going to be a little bit different from what you say. So that's the intuition. And the other answer, the other reason for this is that, remember, P of x between A and B by definition is integral of f of x from A to B, right? Now what happens in this integral if instead of B I put in A? I get 0, right? So that's why in the continuous case, if it's equal to, it's 0. There's no probability. Right? Or, for example, if you're measuring a current in a circuit and that current is a random variable, the probability that that current is, for example, 1 milliamp, exactly 1 milliamp is 0. It's going to be always a little bit different from 1 milliamp, right? Because there are infinite numbers, right? They're not just, you know, discrete number of milliamps, right? So assuming that we ignore the quantum, you know, quantum mechanics and all of the, you know, so apparently even time is quantized, right? So it's not a continuous random variable, but we are ignoring that, right? We are assuming that time is a continuous random variable, for example. Yeah, and for the discrete case, this is not correct anymore, right? Because if x is discrete, then there's a chance that x is exactly x, right? This can be non-zero. Okay, so that's the first thing. So basically, this means that discrete and continuous are different domains, right? So the second thing is that approximating a discrete distribution with the standard normal distribution. The first thing is that, you know, check if it's less than or if it's less than or equal to. Sorry, I wrote on the following test. So you have to check what the question wants. Does it want less than something or less than or equal to something, right? But if you're, you know, looking at the normal distribution, right? So if somebody tells you, oh, you're looking at the normal distribution, so x is a continuous random variable and, you know, its distribution is normal, then P of x less than x and P of x less than or equal to x are the same thing. You know, since x is continuous. So I hope I didn't confuse you. I hope I helped you. But I haven't yet explained why we add 0.5.
So what would be the difference, like if we are anyways converting it to a standard normal distribution, pay it to make sure that it's less?
So basically, like, for example, if we go back here.
It was less or equal, I think.
Yeah, so here, right? So the question said, what's the probability that 950 or fewer particles are found, right? So assume that the question said, instead of 950 or fewer, it said that find the probability that less than 950, right, are found, right? So in this case, remember that the equation we have to use is that now I have to say, okay, P of x less than or equal to 949, right? Because it's, if you want to apply the continuity correction, this guy has to be less than or equal to. It can't be less than. So you add 0.5 and then apply the continuity correction. Sorry, you subtract 1 and then you add 0.5. X less than 949.5 because it's less than 95. 950, sorry. Yeah, so basically like this 0.5 is sometimes it doesn't really matter. You know, for some probabilities, when you look at, you know, when you calculate this guy with and without 0.5, you see that you almost get the same answer, right? So if it's bothering you very, very much, you can just forget about it because the answer you get most of the time is going to be quite similar. Okay. Now, let me explain why we add the 0.5, right? So I think I really thought about this example. So I think you can, if you pay attention, you can find out why, basically, you can understand why we add this 0.5, right? So assume that we have a simple case, right? So we have a discrete PMF, and the probabilities are, we can either get a 1 or 2, right? So our x, our random variable, has two values of 1 and 2, right? So let's say it's a coin with two numbers on it, 1 and 2, right? So I'm flipping that coin. And for some reason, probability of flipping 2 is higher, right? So probability of 2 is 0.6, probability of 1 is 0.4, right? So when I convert this to a continuous x, so this is x, so this is x discrete, and this is x continuous, right? So when I convert it to a continuous x, this is how it's going to look like. So this is again 0.4, and this is 0.6, right? And this number right here is 1.5. So if I told you, in this discrete case, calculate the probability that x is less than or equal to 1, right? You're going to say, oh, okay, that's equal, basically what you want me to calculate is probability of x equal to 1, and that's 0.4, right? When we move to the continuous case, we have to look at the area under the curve, right? The area under the curve that we are going to look at is actually this area, not the other one that I'm going to plot in green. It's not this one, right? It's the purple one, right? And the purple one is in fact also 0.4, right? So that's why we move forward by 1.5, because in the continuous domain, we are happy if our x is 1, but we are also happy is all the way up to 1.5, right? How many of you got less confused with this? Yeah, okay, that's not bad. Is there anybody who wants me to explain this again? It's not in the book, but I think it is important. Yeah, okay. Yeah, so I can explain again. So basically, the setup is, a coin that I'm flipping. The coin has two numbers on it, 1 or 2, right? Probability of 1 is 0.4, probability of 2 is 0.6, right? If I want you to calculate probability of x less than or equal to 1, and x is the number that we get after we flip the coin, I guess we agree that that probability is 0.4, right? Because this guy is 0.4, right? Now, if I approximate this with a continuous PDF, right, what I'm going to get, this is a little bit beyond the scope of this course, but what I'm actually doing right now is called nearest neighbor interpolation, right? So I'm going to interpolate this. So I'm going to say, oh, okay, up to 1.5, the probability is 0.4, and then after that, I'm closer to 2, so the probability is 2, right? So this is 0.5, and this guy here is 2.5, right? So this basically, this green curve is x continuous, right? If I have a continuous random variable, the probability of that continuous random variable being between 0.5 and 1.5 is 0.4, and being between 1.5 and 2.5 is 0.6, right? And now what I'm going to say is that, okay, you want me to calculate, in the discrete case, you wanted me to calculate probability of x being less than 1. In the continuous domain, 1.4 is also approximately 1, right? So in the continuous domain, if x is 1.4, or it's 1.3, or, all of these numbers that are less than 1.5, they are still counted as 1, right? So that's why I add 0.5. I say, oh, I look at the middle between, 1 and 2. The middle is 1.5, and I go forward by that much. Right? It's sort of like, yeah, okay, now I know. So it's sort of like when you calculate you round up numbers, right? when you round up, 1.2, it basically gets converted to 1, but 1.9 gets converted to 2, right? So that's why.
So this explanation would work only for like consecutive natural numbers, no? If the die had like, for example, 0.1, 0.2, 0.3, right?
Still works.
But 0.5 would go to plus 0.5 would go to 0.6, let's say.
Yeah, still works, but for that it's much more complex. We have to, if you want, we can discuss after the class. But it does work. This is basically, you're right. This is it's a very special case, but the idea is always the same, right? We have to make some changes, right? But after we make the changes, it still works. Yeah.
So in case for the dice from like 0.1, 0.2, like we can add 0.05.
Yeah, exactly. Yeah, always the middle, right? So if the dice, for example, is not 1 and 2, is like 0.1, 0.2, 0.3, again we have to look at the middle between the two. Yeah, it's the middle. Yeah, you're right. Yeah. But remember, for the discrete PMF, our x is you're right. It can be 1.1 and it still be discrete, right? You're right. Other questions? Okay. So the next distribution is the exponential distribution, but it's not really a new distribution. It basically is a byproduct of the Poisson distribution, right? So remember that the Poisson PDF was this, right? And here x is discrete, meaning that x is either 0, 1, 2, or 3, right? So x is a discrete number. Now, if I define a new x that equals the distance between successive events of a Poisson process, then the distribution of x is an exponential distribution. And the PDF is the following. So, for example, if you look at the midterm exam, since all of you are very familiar with that question, so the number of potholes on a street, let's say, is modeled by Poisson distribution, then what would be this exponential distribution in that case? Raise your hand if you know the answer. So the question is, the exponential distribution is defined for x, where x is the distance between events of a Poisson distribution, right? So I want to give an example for that, right? So assume that the number of potholes on a street is a Poisson distribution, right? Let's say with a mean of 10. So per kilometers you have 10, right? Define x such that x has the exponential distribution. What is the non-random variable that is exponential in that case? Because the number of potholes is Poisson, right?
The distance.
Exactly. The distance between the potholes, right? So that would be, for that case, the distance between the potholes would be the exponential distribution, right? Or if we are looking at for example, the number of customers that visit Tim Hortons, what would be the exponential distribution? Yeah. Say it again. Exactly. The time between two customers, but the time until, for example, the next customer arrives, right? That would be exponential. So in fact, exponential is quite, is linked with the Poisson, right? So we have the equation for the mean and the variance, right? And remember that for the Poisson process, mean and variance were the same, right? So lambda was mu, and v was also mu. V was not mu. Mi was also lambda, right? Here it's a little bit different. So mu is 1 divided by lambda, and variance is 1 divided by lambda squared. So meaning that mean and standard deviation are the same. So the mean always makes sense. So we can try to understand why the mean is 1 over lambda, right? So for example, if we look at the midterm exam, right? So number of potholes is a Poisson with lambda equal to, for example, right, 10 per kilometers, right? So let's say there are 10 potholes per kilometer, right? So that means that if I define x as, how far I should drive until I hit the next pothole, right? So distance until next pothole, right? Then this equation tells me that the expected value of x is going to be 1 divided by lambda, or 1 divided by 10 kilometer, or 100 meters, right? And it does make sense, right? If you have 10 potholes per kilometer, the distance between them, is 100 meters, right? So here, if lambda goes up, then the expected value goes down, right? Meaning that if you have more potholes, then the expected value of the distance between the potholes goes down, right?
But then aren't we assuming that the potholes have the same distance between them?
What is it?
Aren't you saying that?
No. Yeah, that's a very good question. So the question is, am I saying that there is a 100-meter distance between the potholes? No, I'm not saying that. I'm saying that in average, the potholes have a 100-meter distance between them. But, there can be 2 potholes right next to each other.
So,
Yep.
can you scroll back to the equation for the distribution?
Yeah. This guy?
In the crib sheet, it's written 1 over lambda, and it's called beta.
Yeah, so you can define that, yeah. But it's the same thing at the end.
No, I'm saying in the crib sheet, it's beta equals 1 over lambda, and it's written 1 over lambda, exponential 1 over x over lambda in the crib sheet.
Yeah, but I think it should be the same equation at the end. We can talk after the class. It must be the same. The crib sheet you're saying that the crib sheet defines beta as 1 over lambda? Yeah, so that could be the case. You can.
In the distribution, it's beta exponential minus x over x.
Yeah, you can define another parameter beta, which is 1 over lambda. But at the end, it's the same thing as here. I don't want to go to the crib sheet because it will damage the video. Other questions? Yeah. Yeah, that's a very good question. It's the same lambda, right? That's why, if the crib sheet has beta, I don't like it because it's introducing another parameter. We can use the same lambda. Okay. Yeah. Okay. So basically, if we want to summarize, what we have learned is that first, like if we want to approximate something with a normal distribution, the first thing we have to do is we have to find out what is the distribution, what is the original distribution. Is it basically our goal now is to convert things to the standard normal distribution such that we can use the table, right? We have the table for the standard normal distribution, right? So we have to find out where we are starting from. Are we starting from a normal distribution, right? For that, we have to use x minus mu divided by sigma. We have to see if we are using the binomial, right? And for that, we have to use x minus np divided by square root of np times 1 minus p, and for the Poisson, right? That was another question, right? But I mentioned all of them at the end is this equation. Right? And then once we figure out, what is the original distribution, then we have to find the mean and the variance of that distribution, right? So mean and the variance, sigma squared. And then we have to use this equation, right? Once we subtract the mean and divide by the standard deviation, we get z, where z is the standard normal. So always, this is denoted with z. Right? Whenever we write z, we mean that is standard normal. And one note here is that, I mention this every year, but still I see many mistakes in the exams. You have to divide by sigma, not sigma squared, right? So if you're calculating the variance, then you have to get the square root of that and divide by that. And then once you have these, right, the rest is super easy. You have to look at the table for the z that you got. And that's why I think this chapter is really simple, right? Once you get the idea, it's really, really simple. Much easier than counting techniques, which can be quite tricky. Much easier than calculating the probabilities using some distribution, which is difficult because you have to figure out which distribution to use. So I think this chapter is really easy. So, for example, if we look at this problem that we solved, we had the probability of success was 10 to the minus 5, and n was 16 million, right? We converted to the standard normal, and then at the end we got this z, and then we calculated the probability of this z using the table, right? So since Poisson and exponential are similar, I like to put them side by side so that we can review them again to see what's the difference. So random variable x in the Poisson distribution is the number of events, and this is the PDF. For the exponential distribution, random variable x is the distance between successive events of a Poisson process, and this is the PDF. Okay, so let's look at an example to see how we can use the exponential distribution, right? In a large corporate computer network, user logons to the system can be modeled as a Poisson process with a mean of 25 logons per hour. Right? What is the probability that there are no logons in the next 6 minutes? Right? So in average, there are 25 logons per hour. We want to see what's the probability that 0.1 hour passes by and there is still no logon, right? So this curve here is the PDF for the exponential distribution. Remember, if we look at the exponential distribution here, the largest value that this curve gets is always at x equal to 0. Right? Because this is an exponential function, right? So this function always looks like this. Oh, sorry, it doesn't go up. It basically decays exponentially, right? So always exponential distribution looks like this. So I want to calculate the probability that the next login happens after 0.1, right? So I want this area under the curve. And this area under the curve is p of x more than 0.1. That means integral of the exponential distribution from 0.1 to infinity. Right? And remember that integral of lambda e to the minus lambda x is equal to minus e to the minus lambda x, right? From a to b, from a to b, right? This is from calculus, right? Integral of lambda e to the minus lambda x is minus e to the minus lambda x. Right? So here I have used this equation. And at the end, we get 8%. Right? There's an 8% chance. Is there any other way we can do this? We can solve this question? I think there is. Any ideas? I think we can solve it another way. Right? Yeah.
Do we normalize it?
Yeah, so we can instead use I think we can use the direct Poisson distribution, right? So let's see what happens. So the question says, we don't want no logins in the next 0.1 hours, right? So in 0.1 hours, what is the average logins? So lambda is 2.5 logins in every 0.1 hours, right? So we normalize it. And then, so this is another solution. So now I'm going to say what is probability of x being equal to 0, and x here is Poisson. Oops, what happened? Right? And that's equal to x factorial e to the minus, I don't remember the equation. So e to the minus lambda to the power x, right? E to the minus 2.5 lambda to the power x. It doesn't matter because x is 0, so that's going to be 1, and then 0 factorial. So the answer is e to the minus 2.5. Does anybody have a calculator?
Yeah.
Check this, whether this is the same answer. E to the minus 2.5. What is it? It's the same thing, yeah. So yeah, we got the same answer. Right? So you see, they are actually the same thing, Poisson and an exponential. Any questions? Was this clear?
So why did you make it equal to 0?
Yeah. So basically the question says, what's the probability that there are no logins, right? So now what I'm going to do in the second part, I'm going to define x. So in the top part, x was the distance, right? That's a very good question. I should have written this. So in the bottom part, I'm going to define x as the number of logins in 0.1 hours, right? So I'm going to define my random variable x as the number of logins in 0.1 hours, right? And now I'm going to calculate probability of x equal to 0. That means that no login in the next 0.1 hours. Any questions? Yeah, I know this is a, you can think about it later at home. I know it's a bit convoluted. So basically the x here is the time. So at the top, the x is the time between logins. The x at the bottom is the number of logins. So they are different x's. Okay. So continuing, what's the probability that the time until the next login is something in between 2 and 3 minutes? Right? So I want to calculate the probability of x being between, and you see here, I don't care whether it's more than equal or less than equal. These are continuous, so it doesn't matter, right? So I can add them or I can, drop them. So x more than 0.033 and less than 0.05, right? So all I have to do is to calculate this integral. That's the exponential distribution. Again, what I'm doing here is that I have this exponential distribution. This is 0.033, and this is 0.05. So all I'm doing here is that I'm calculating this area under the curve. And this curve here is 25 e to the minus 25 x. And this axis here is x. This axis here is the PDF, f of x. Any questions? Okay. So let's continue. What's the interval of time such that the probability that no login happens is 0.9, right? So I want to find some interval of time, right, such that probability of no login in that interval is 90%, right? For example, I'm repairing, the service, I'm doing some maintenance, right? I want to see how long my maintenance can take, such that, probability of somebody trying to log in during the maintenance is, 0.1, right? Or probability that nobody logs in is 0.9, right? So if my interval is very large, for sure somebody will log in. Right? So basically what I want is find x such that probability that x is more than x is 0.9, right? So if I again plot the curve, I want some x such that this area under the curve is 0.9, right? So what I'm going to do is that I'm going to say probability of x more than x is equal to integral from x to infinity of lambda e to the minus lambda x d of x. And as I said before, that is minus e to the minus lambda x from x to infinity. Oh, and by the way, I used the bad notation, right? It's a bad idea to have the argument of the integral and the bounds the same. So here I can use dt, and here I can use t, and here also I can use t, right? Oh, this is better. Okay. And this thing here, if I plug in infinity, I'm going to get 0. And if I plug in x, I'm going to get e to the minus lambda x, right? This is always correct. Right? So this area is always equal to probability of x more than x is equal to e to the minus lambda x for the exponential distribution, right? So that means that my lambda was 25, right? So I plug in lambda, so e to the minus 25x is 0.9. And this is a very simple one equation, one unknown. I take the log of the both sides, and x becomes 0.25 minutes. Any questions? Yeah.
So why do we assume that random variable is bigger than x, or would we try both sides?
Yeah, so the question says, what's the interval of time such that the probability that no logging happens is 0.9, right? So what I said is that, there is going to be, so basically the time, so this axis here is the time that it takes until the next login, and this axis is f of x, the probability of that. I'm going to have some login at some point with this probability curve, right? What I'm interested in is I don't want the login to happen here, right? What does that mean? That means that I want the login to happen here, because there is going to be some login, right? So no login happening, in that interval, it means that the login happens in the other interval. The login has to happen.
So now we're saying on the right side, there's 90% chance that there's no login.
No. So what I calculated is that I said that what I calculated is that the probability that, yeah, you're right. So no login happening in the interval is 0.9. So it means that
from x to infinity,
so that means that from x to infinity, the probability is 0.9. That's what it means, yeah.
But wouldn't there be a chance that maybe from 0 to x also there might be a 90% chance that there will be no login? From 0 to x?
No, basically I want no logins. I want there to be no login between now and basically 0.25 minutes, right? So maybe if let's do the following. What's the probability that x is less than 0.25, right? So we can calculate this guy, right? What's the probability that, for this random variable where my lambda is 25, what's the probability that the time until the next login is 0.25, right? So we are out of time. So in the next class, we can actually calculate this with the probability, and this makes it more clear. Yeah. Any questions?